Good afternoon, everyone. My name's Eli Dart. I'm from ESNet, the Energy Sciences Network. We're a national network that interconnects the DOE National Laboratory Complex. I'm going to talk, we've been talking a lot about what goes on inside the machine and what goes on in terms of the software that runs on the machine. I'm going to talk now about how to get data from the outside world into the computing center such that you can load it onto the machine and analyze it, or how you can export data that you've created on the machine to outside of the computing center. So I'm going to talk a little bit about what science networks are, go into the structure of the internet a little bit and why certain things are the way they are, why science networks matter and why they're different from the commercial internet. I'm going to talk a little bit about data transfer capabilities at the HPC facilities where we all work. And then I'm going to talk a little bit about data portals, sort of where they've been, sort of where we are now, which is in a state of transition a bit, and where some of the things are going for the future. And so actually as a I don't know, use case, if you will, I'm going to grab some data from one of these data portals, which is the Research Data Archive at NCAR. So let's say, hypothetically, I'm a climate scientist, and I've applied for, say, some kind of allocation. Maybe I got an Insight Award, something, but I've gotten an allocation at the ALCF at Argonne, and I need to get some climate data to analyze with that compute allocation. So I'm going to grab some data from NCAR, right? So NCAR has this thing they call the Research Data Archive. And so if you go there, right, you get this thing. And so I'm going to go, I could go browse to it, right? Or I could just, in the interest of time, say, all right, I've already got the data set queued up, right? So here's the data set that I want. Here's some stuff about the data set. This all comes out of the database in the web portal, right? And I look around. It's 1.5 terabytes of data, so it's not small. By my standards, it's not particularly big either. But it's something that with sort of legacy tools might be difficult to manage. So I'm going to go fetch this real quick using Globus. So if I click on the Globus Access link, it gives me a Globus job here with all the data set queued up on the other side. And then, because I've got my allocation at Argonne, I'm going to go pull this down to Mira. Right, and now I'm just going to go drop this in here. Right, so, right, that's fine. So, returning to what we're doing, which is talking about how we're going to use science networks to do what I just queued up. Right, so what is a science network actually? So we're grabbing data from a data portal and we're putting it on a file system at a supercomputer center hooked up to a machine, right? What does that actually mean, right? So I'm downloading this via the network, right? What does it mean to do that? And what is this thing that is the network anyway, right? If I wave my fingers around in air quotes, what is the network? So most of us are familiar with this notion of an internet service provider, or ISP, right? So this is what gives us the internet at home. We can watch Netflix or do whatever on it. It gives us data for our phones, so I can do Facebook on my phone. I can do maps on my phone. I can search for things on my phone. I can do various things. This is what most people think of when they think of the internet or the network, and this is what most people see. And in fact, most people think that what those of us who've been around a while call the World Wide Web is actually the sum total of the internet. It's not, but that's what most folks see when they think of as the internet. So science networks interconnect science facilities in the same way that the commercial internet interconnects commercial things. So this is computer centers, fine. It's also particle accelerators, so the Large Hadron Collider or a synchrotron. There are several in DOE, and data portals like the NCAR RDA that I just visited. And in fact, science networks use the same set of protocols as the commercial internet. They predate the commercial internet, in fact, as some of you may know from your history books. And we're connected to the rest of the internet as well. So in some cases, we're similar to internet service providers, or ISPs. So if you look at this is a picture of the ESNet footprint, right? So we've got a state-of-the-art fiber optic network. It's deployed across a whole bunch of places in the United States. There's 340 gigabits across the Atlantic in 4 circuits, and we've got a ring in Europe as well, which gets us to a bunch of European sites, including the LHC at CERN. But we're not to first order an ISP. We look like one in some cases, and we carry web and email and all that kind of stuff. But that's not the reason we exist, right? We exist as a scientific facility specifically to further data-intensive science. And doing that requires some special engineering, which means there's some stuff that we need from a network in order to do data-intensive science that the commercial internet doesn't necessarily provide. So let's talk a little bit about the difference then between the commercial internet and some science networks, right? So what is the internet really? So internet is short for internetwork. So it's a network of networks, right? It's a set of networks that are connected together, each for their own reasons. So, and this is just a random example of things that folks may or may not notice or know about when I put the text string up there, right? So everybody knows who Google is. Everybody knows who the military is, right? Ford Motor Company has a network that they run for their own purposes. The DOE does too. Hi, that's me. And AT&T, whomever, right? So everybody's got a network. It exists for whatever reason they built it for, right? So I need a network to do stuff, right? So I build a network. And then if it's useful to me, I connect that network to other networks. And I don't know if you've heard about this notion called the network effect, right? But in general, networks are more valuable when they're connected to other networks. But that happens for selfish reasons, right? I do that with my network for my reasons because it helps me. And there's this sort of emergent behavior, right, where the internet's this really useful thing that humans have managed to invent for themselves, but the different individual components are the way they are because the entity that built that component needs it to be a certain way for a certain reason. So not all networks are the same. So this is drastically simplified, but it serves to illustrate the point. So we've got a bunch of different networks here, and they're all sort of invented and deployed for their own reasons. So if I look over here, right, here's Google, right, and they provide some services, right? They provide a search service, they sell ads doing that, they make a lot of money doing that. They got YouTube, Gmail, a bunch of things like that. Now really what's Google got connected to it, right? It's got a bunch of these giant data centers connected to it, and those are the things that provide those services. In order to consume those services, people need to get to Google's network, but they're not directly connected to Google's network, right? So my iPhone is connected to AT&T, right? So my phone's connected to AT&T's network. I couldn't get to Google if AT&T were not connected to Google's network by some means. Now, it turns out Google and AT&T are both kind of important, and so they're connected to each other, as the diagram shows. If that connection weren't there, AT&T would have to go through a third-party internet service provider, which connected to both AT&T and to Google in order to get to Google, right? And you can generalize this broadly, and it is generalized broadly. So there's a couple of examples over there of other entities that might be connected to this internet service provider, right? Some car company, maybe an insurance company, maybe a bank, maybe whomever. So the commercial internet is a set of folks providing services, a set of folks connecting other people to those services, and folks who want to consume those services buying connectivity from an intermediary usually. So the stuff that's shades of blue is the set of science networks. Now, they're connected to the rest of the internet, yes, but they're their own separate entities built in their own ways for their own reasons. So there's ESNet. Connected to ESNet is a bunch of DOE labs and DOE facilities. There's an analog of ESNet called Internet 2 for the university space. They connect a bunch of regional networks which have universities connected to them and so on. So that's a drastic simplification. So if you want to see how complicated the internet really is, there's a URL here in the slide deck to some analysis done by CADA. And they've been doing this for years. They have a bunch of really nice visualizations. It's pretty neat to look at, actually. But the thing to remember is that all these different networks exist for their own selfish reasons, right? They provide connectivity either for themselves or for others as a business model, maybe not. Maybe they provide services, whatever they do. And in some cases, those lines are blurry, but that's a good way to think about it. So the reason a network exists then has some influence on how it's built and how it's run and what capabilities it has. And so not all networks are actually good at supporting all use models. And in particular, for science networks, we have a different traffic profile than the commercial networks do. And so we're engineered to handle that traffic profile, not a bazillion web browsers and phones and little YouTube streams. So how is science data different than commercial? Often it's just the size and speed of the data flow that you have to handle. So we talk about this in terms of elephants and mice, just because it's descriptive. So if you think of a thundering herd of elephants, what is that? It's a lot of mass moving at the same time, and each one of them is pretty big. Mice, on the other hand, if you have a large number of mice, you can end up with the same amount of mass. It's just composed of a much larger number of tiny little entities. And so what that looks like in terms of network traffic turns out to be pretty different. So the picture on the left here, this is some data taken from ESNet's network, right? So the blue line is regular routed traffic. The lower line here is our virtual circuit service. But if you look, there's a lot of variability, and there doesn't seem to be much of a distinct pattern to it. The diagram on the right, this is a rate chart from a large internet exchange. And I'm sorry for the eye chart, but if you can see the y-axis there, the top of these haystack peaks right here is about 1.4 terabits per second. So there's a lot of data going through that exchange point. Most of it's composed of these tiny, tiny, tiny little flows. And you can see that in the profile over time of day, right? So that's time of day on the x-axis there. When people are awake, there's a boatload of traffic. There's a lot of activity. When people go to sleep, so does the network, right? And I mean, I like to call this a web and email haystack, right? Because when people are up, they're sending email and they're browsing the web and they're doing whatever they're doing. When they're asleep, they're not, right? And engineering a network to handle this sort of traffic profile is very different from engineering a network to handle large-scale data transfers between scientific facilities. So what do elephant flows actually look like, and what does it mean to engineer for these things? So I'm going to use the notion of water plumbing as a crude analogy here. But say you had a physical pipe, right? I'm carrying water, and it leaks at some small rate, right? So what do I do, right? I end up with most of the water delivered to the other side, but the fact that there's a leak in the pipe doesn't particularly affect the pipe's ability to deliver the water from one end of the pipe to the other, right? So far, so good. If I have a network that has 0.0046% packet loss in it, I turn an elephant into a mouse. Now, the whole mouse gets through eventually, right? All the data will actually get there, but it gets there really, really slowly. Why does that happen? Turns out it's based on the governing dynamics of TCP, which is the reliable byte stream delivery protocol of the Internet Protocol Suite. This equation was developed by Matt Mathis and others. But the thing that we can affect in this, right, so this is, the throughput is related to the maximum segment size over the round trip time times 1 over the square root of the packet loss rate. Most of those things we can't affect, right? So the maximum segment size, right, the largest packet you can send over the internet is largely fixed. You can use jumbo frames or not, but other than that, it's basically fixed. Round trip time is governed by the speed of light. If you can fix that, there's a Nobel Prize for you, and that would be lovely. You should get right on that, and we will be delighted when you fix it. Until you get that Nobel Prize for fixing it, we're kind of stuck with that too. And so the only thing that we can really affect in order to improve on network performance or network throughput is the packet loss rate. And so how important is the packet loss rate? How much does this matter? A lot of the text describing how much it matters fits on the plot between the happy line and the sad lines. So here, this is some data from ESNet, actually. I found a line card that was having some problems, and it was causing some packet loss. And before I fixed it, my friend Brian Tierney said, wait, stop. Let me measure it. So I waited, and he measured it. And that's all the sad lines down there, is measurements. And also there's the theoretical there, the dashed green line, is what the Mathis equation that I showed on the previous slide would predict. But this purple line up here is without packet loss. The y-axis is linear, 0 to 10 gig. The x-axis is the round trip time in milliseconds between the communicating hosts. And the interesting thing about this is, so this has several important implications. One is within your campus, within your sort of local area, you can have packet loss up to a point, and it won't really affect your performance all that much. Once you get into the same metro area, yeah, it affects your performance some. Use a couple parallel streams, you're back up to full rate, no problem. Once you get out of your metro area, you've sort of fallen off the cliff, and it just doesn't get better from there. And if you have to go across an ocean, it's really bad. And so look at the loss figure, though. All right, so 0.0046% packet loss, that's about 1 packet in 22,000. Right? So if somebody tells you 1% packet loss, how bad can it be, right? Wrong order of magnitude by like a bunch. So how do we fix this? One of the more reliable fixes for this has been something that we call the Science DMZ model, which is a set of network design patterns for building the data-intensive science portion of a network. So this is deployed at the supercomputer centers in DOE, for example. There's a particular enclave of the network, typically built at or near the network perimeter, where it's built out of high-performance components, and it houses what we call the data transfer nodes. These are the hosts whose job it is to run the data transfer tools and mount the file system and do data ingest and export from that file system. There's a network monitoring infrastructure called PerfSonar that's integral to this. I'm not going to go into that here because I don't expect you all to be working as system administrators or network administrators running this stuff. This is the sort of thing where if you run into problems, you can tell your sysadmins and network admins to look at this stuff and if needed, send them to me. And I will help them help you. But this is widely deployed at this point, which is good for all of us. So it's over 100 universities. The National Science Foundation has thrown a bunch of money behind this. It's international as well. And there's a URL down there for it's the portion of our knowledge base site, fasterdata.es.net, that describes the Science DMZ model. So that's what helps reliably get around this notion of having a bunch of packet loss that kills your data transfer performance. So then, once we've got that in place, we can start building things on top of it. So built on top of this, I and some people at several supercomputer centers recently did what we call the Petascale DTN project, which was to improve the data transfer performance between the 3 Office of Science computing centers in DOE and also NCSA. And so this was, we picked a reasonable target performance goal right at 15 gigabits a second. That gives you about a petabyte a week in terms of data transfer performance. So you can move a lot of data with that, provided you have a tool that deals reasonably. And we do. All those centers run Globus. And so the test data set that we used for this was some real simulation output. It's not lies and benchmarks, but it's real simulation output transferred using a Globus job with the defaults turned on. And the answer is, at this point, things work pretty well. So there's only one of these pairwise transfers that's below target at this point, and that's from NCSA to NERSC. Everything else is above target, and we're working on that last piece. But again, if you look at it's hard to read again, I'm sorry, but if you look at the composition of the data set down here, it's not a perfectly constructed data set for benchmarking purposes, right? It's 19,000 some odd files, over 200 directories, and a wide range of file sizes. So this is real model output, and so this is the hope is that users would see this sort of performance when they're doing normal activity, transferring data between computing facilities, or in fact between data portals and computer centers. So speaking of data portals, what's a data portal, right? So again, we're going up the stack now, and so now I've got, what do I have? I have a bunch of data, and I want to publish it. I want to make it available to data analysts so that they can move it to HPC facilities and do productive work on it. I could have any kind of data in there. Climate data, we saw, sky survey data for astronomy and cosmology. It might be genomics. There's a bunch of different science domains that all have data portals that provide for finding the data, browsing the data, accessing the data. The tricky thing is a lot of these data portals were designed on the order of 15 years, about Y2K. And so at that time, what happened was, and remember, at that time, the state of the art was command line FTP. And so Apache sort of got good enough. We got CGI scripting, which was great, and some database integration with CGI scripting, which was also great. And someone realized, hey, wait a minute, I can put together a little database with my metadata in it and my users in it, and I can do some CGI programming, and I get a GUI interface for free in a web browser. I don't have to implement a GUI at all, and poof, I have a graphical interface to my data repository, which is way better than the state of the art, which was command line FTP. And so that was great. A lot of data portals sprung up. They've been very productive. People got a lot out of them. They have not changed since then, most of them. In fact, they've only become more complex. They don't tend to perform much better. And the reason for that is people are still dragging data objects through that web server, right? And so if you look at what this means, right? So somewhere in here, I've got a file system. I've got a web server there. And I'm going to drag all of the data objects, which are now much, much bigger than they were back in 15, 20 years ago, right? I mean, people have terabyte and bigger scale data objects now. I'm going to drag those through an Apache server. Awesome, great design. And so if I want to accelerate that, right, and make it go faster by putting it in a Science DMZ, now I have another problem, which is that data portals are these complex web services applications. And so the security profile of a Science DMZ isn't well suited to defending complex web applications. It's really well suited to defending DTNs, but it's not super great at defending against SQL injection and all the other kinds of modern security threats that afflict things like data portals. So if we want to make this go faster, we need to do something else, right? I mean, we can't brute force our way out of this, right? We got to think our way out of this. So what does that mean? All right, so we need an architectural change to do this. So what does an architectural change mean? How might we decompose this? So if we look at what other portions of the internet have done to change themselves architecturally, we can look at, as an example, at what content delivery networks did for web applications, right? And I mean, in this case, simple web browsing. So this is a well-deployed design pattern. Examples include Airbnb, the Olympic Games, whatever. What does it do? It takes apart the notion of a web page and puts the static content in some place that's close in network terms to where your browser is. And it allows the web server, wherever the web server happens to be, to serve you the web page. But if you look at the contents of a web page, what is it, right? It's a text file. And in that text file, there are pointers to all the other things that are going to be rendered along with the markup in the text file. And so the web server just goes and fetches those other things. Well, they can come from wherever, right? They can come from a third-party ad provider. They can come from a different web server. They can come from someplace completely different, right? So that's what they've done. And so instead of this classical web server model where I download the thing from the web server wherever it happens to be, and remember the TCP loss plot I just showed, right? In this model, all of the large-scale data objects coming from that web server are subject to all the problems that you might see in a long-distance network if there's packet loss involved. And let me guess, right? These days, we're all on wireless, right? So our wireless, is Wi-Fi loss-free? I didn't think so, right? So you don't want to stick that in the middle of all of this with long-distance, high-latency stuff. So what do, right? We just take the web page apart. And as long as we keep our cache consistent, nobody has to know that we took the web page apart. But we did. And this has been, like I said, this is a well-deployed design pattern. This has been in place for a long time. It works great. And so what does it mean, right? Time to page render goes way down. Performance for static content goes way up. It's a big win. So if we look at data portals now and we say, all right, what I'd like to do is figure out how to do the same sort of architectural decomposition that the commodity internet folks did for doing web pages better. What can I do? How can I take this thing apart? So one of the things I can do is say, all right, well, I've got a list of functions that my data portal has to perform. Search, data download. It's nice to have a GUI for the humans to use. It's also nice to have an API interface for machines to use, right? A machine consumable interface is really productive, right? So that's awesome. Maybe I want one of those too. And really, where's the part that hurts, right? The part that hurts and the part that's hard is in the data handling piece. So if I can put that someplace else, that might be a huge win. So can I do that? The answer is absolutely. So we've got a science DMZ over here. We've got a cluster of DTNs over here that can serve static data objects all day long. Throw them on the wire, they go great. So we can leverage that. So here's our old school data portal, and then here's what we do to it. We take the data handling piece, right, just the static data objects, we stick them on a DTN cluster over here, and that web portal doesn't have to know or change. It has to change initially, which is to say, instead of serving up URLs that point back into itself, it serves up URLs that point over there to the science DMZ, and now we're done. Right, and this, in fact, is what the NCAR RDA has done. Right, they've done exactly this. So what have we done then? We put the data handling piece on dedicated infrastructure designed for the purpose. The portal still gets to be its own happy database integrated GUI self. We can run it wherever we want. We can stick it in Amazon if we want. Right? It really doesn't matter. And the high performance data handling piece now runs on stuff that we've designed for the purpose. And in fact, in many cases, this can run at a supercomputer center because supercomputer centers are good at handling large scale data objects. They've got DTN clusters to deal with that. So data portals have a lot of valuable data in them, right? That's a huge scientific value. Most of those have been in place for a long time. It would be great to be able to upgrade them. Some of them are being upgraded, and that's great. If you run in, so some of them that you run into are going to be this sort of higher performance model. Some of them are going to have really clunky old interfaces. And so asking whether they have DTN access for the data in the data portal would be useful. And in fact, if they don't, and you think they might be amenable to trying, I'd be happy to talk to them about how to get that going and maybe do a trial run. So the HPC facilities are set up for this, right? The data portals should be as well. So looking back then at the data download performance from the NCAR RDA, right? This is what I've seen to the different DOE computing facilities. And actually, let's go see what happened here. So I had this, and I kicked this thing off. So this ended a while ago. All right, so I just pulled down 1.5 terabytes while we were sitting here talking. A little over 2 gigabytes a second. It took 12 minutes. Right? So if you design it right, it works just fine. You can blow your entire storage allocation really quickly, pulling down data to analyze at a computing center if you use stuff that's actually designed and built correctly for the purpose. I guess in summary what I'd say is, just to remind you of the main points, right? There's a set of science networks that are separate from but connected to and related to the rest of the internet. And that's what we try to put all the large-scale data handling stuff on. We try to plug all the large-scale data handlers into a science network. You can orchestrate that from wherever you want to orchestrate it from, and that's okay. Part of how we do that is using the science DMZ model. If you need your system or network administrator to talk to me or talk to ESNet about implementing a science DMZ at your institution or for your project maybe, let us know. I don't guarantee success. I have no hard power here, but I'm happy to talk to anybody about this and see if I can help get something off the ground. One of the things that makes this really valuable is the use of a capable tool such as Globus that makes it possible to sort of get your hands around the large-scale data objects and move them. And in fact, Greg's going to follow me, and we're going to hear more about Globus here in a minute. But there's a key point there that deserves belaboring a little bit. So humans scale terribly. Right? I scale badly. I'm sure all the rest of us do too. And we live in an exponential world. And so what we really need is a tool set where the effort required to handle data sets that are constantly growing in size and scale, where the effort required to do that does not scale with the data. Right? Because if the effort level scales with the data, we just lose. Right? Because I don't know about you, but I can't scale to that. And so the thing that's important then is to be able to have a tool set that scales and built on an architecture that will handle it. And I would say there's a huge opportunity in upgrading data portals using this model. And again, if I can help there, I can. So reason we do all of this, right, the way we look at the world is we want science to be unconstrained by geography. And the only way that works is by making sure everything's well connected together and the data that needs to be wherever it needs to be can be placed there regardless of wherever it is now. So with that, I'm happy to take questions. What are your questions? Yes?
So the CDN might work well for small to medium-sized files, but how will they work, or how might you have to change things to work with files like 100 to 500 gigs?
And so I wouldn't expect the CDN model to work with that well with that at all, right? So I mean, that, you know, I put that in there as an example of architectural change, and there are some cases where some folks are thinking about using CDNs for scientific data. The case where that works well is if you have a large number of people at a variety of different sites which are sort of geographically distributed, and you can replicate the data to file systems that are close to the places where they would need them. Because then you don't have everybody pointing at this sort of central location. You can make the argument that the LHC experiments do something similar to that, in that the different analysis sites that the LHC experiments have, they have storage systems there. And when I replicate a file, I pull a file down off of your storage system, say we're both LHC tier 2s, right? So I pulled some data off your storage system. That updates the metadata catalog. And so now it knows that I've got a copy too. And you know, until I purge that copy, right, we've both got it. So if somebody close to me needs it, they might fetch it from me instead of fetch it from you. And so that's sort of CDN-like in a way. But if you look at, I seem to remember somebody looking at whether this would work for climate data, and the answer is it doesn't work as well for climate data because the different data analysts that consume those models all need enough different things that you can't get good replication scale for that. So it depends. The CDN model works well in some cases and not in others, and there's just an inherent scalability in terms of the size of the data objects. How big a file system do you really want to deploy, and how many of them do you really want to deploy? Right, and so for the sciences, it's often better to have a smaller number of really big data centers with appropriate tooling. And that's sort of what the community seems to be coalescing around. Yes?
What's the approximate cost to set this up that way?
So it depends on what you've already got. So a bunch of universities have they already have science DMZs, and this is because of the very successful CC Star, NSF CC Star program. So it started out with CCNIE, then CCIIE, CCDNI, and so it's sort of changed its name over the years. It's now just called CC Star. But this was a program within the National Science Foundation to fund universities to deploy cyber infrastructure. A lot of them built science DMZs with this. So this has been over the past 5 years. Starting from scratch, if you've got nothing, so those grants were $500,000 to $1 million. And a lot of them bought a nice border router, a nice switch to go behind the border router, a 100 gig circuit to connect them to their regional or to Internet 2, and some data transfer nodes. But if you've already got a bunch of that stuff, right, then of course you don't have to buy that. And so if you have a good connection to your facility or your department or your building or whatever, or your university would allow you to co-locate your DTN in some of their data center space, maybe you just need a nice Linux box and some storage. That you can get for $20,000 to $50,000, depending, again, on what you need to buy. So the cost range is pretty broad, depending on what you've already got. Yes?
So maybe that's already going towards the next talk, but with Globus not being continued as open source in future, how is that going to affect like the entry-level threshold for smaller institutions to get involved, or also with respect to having personal endpoints?
So I'll let Greg talk about that in his talk. My understanding is that the transfer piece is still free, but let's defer to Greg. I'll have you ask him that question after his talk. Yes.
You were saying that these old-style science portals have security issues because of the interface. Exactly how does this solve those?
So the old school science data portal doesn't have security issues inherently, but and what I didn't do is go into a detailed science DMZ talk. If I had, one of the things that I would have covered is the difference between what you can do for security to defend a data transfer node and still have your security architecture be performant, and what you can do to defend a complex web services application and still have your security architecture be performant. And so the kinds of things that you can do to defend a DTN, right? Because a data transfer node's traffic is really simple from a network security perspective, right? What am I going to do? I'm going to open up 4 to 8 sockets. I'm going to write a terabyte across each of those sockets. I'm going to close them, right? That's it. It's like dirt simple from a network security perspective. A web services application like a data portal, you have to deal with SQL injection. You've got who knows how many rendering libraries. You've got toolkits. There's a whole bunch of stuff. And by the way, that's where the sweet spot for malware and attack tool developers is right now, is dealing with things that look an awful lot like a data portal. And so that you can't really defend just using a set of access lists or layer 3 and 4 filters like you can a data transfer node. So it's not that the legacy data portal model is inherently insecure. It's just that it's a bad fit for deployment inside a science DMZ where you may not have the same level of IDS and deep packet inspection. There's a question up here.
Yeah, it was on a similar vein.
Okay.
As that is like, so when you offload static data to the CDNs, they're somewhat, like I've seen, like Netflix can be susceptible to like very distributed denial of service attacks or something like that. Are there unique concerns with that simple traffic model?
I mean, so it's always possible for anyone on the internet to mount a denial of service attack on any particular service on the internet. In general, first of all, we don't tend to see that in our space as much. We would mitigate that in the same way that we would mitigate a denial of service attack against any service, right? And we're actually set up to do that. So you know, that's no different to first order. I don't think that there's anything inherent about this distributed model that makes it any more vulnerable than any other network service to those kinds of attacks. Other questions? Yes?
What about researchers in Asia and Africa? Are they out of luck? I don't see any fast connections to those continents.
So that's just ESNet. And so if you go back to my super crude and simplified version of the internet that shows the interconnections between different networks, we actually have excellent connectivity to Asia, primarily via a set of circuits funded by the National Science Foundation. There's also good connectivity to Africa, as good as there can be. Unfortunately, the African continent's a little bit behind in terms of its network deployment. South Africa's gotten pretty good, and there are other bright spots as well, but there's still a lot of effort in bringing that continent up to par. But we have connectivity to Asia and Africa via a variety of means. Australia as well. So I mean, this gets into what we call peering arrangements, right? Which is where my network connects directly to your network such that we can exchange traffic for the benefit of both of our users. And so we have those agreements with science networks all over the world.